Alex is a returning speaker, and last time he gave a talk alongside August on ZLS, the Zig language server, which is considered an invaluable tool by many Zig programmers. Since then, Alex has become part of the core development team, and let's not forget, all of this while working as a civil engineer in Greece instead of handcrafting pre-processed CSS in a food review startup in Silicon Valley while sitting in a Starbucks and sipping on a pumpkin spice latte. Well, the title is a practical guide to compile time evaluation. So, Alex, the stream is yours.
Thank you very much for the kind intro. So today we are going to be talking about compile time evaluation in the Zing language, also known as CompTime. The goal of this talk is to introduce some of you to some of the more advanced features and the semantics of CompTime, and how you can use it not just to build generic types, but in general to do more interesting stuff. So first off, we will start with one of the core differences between runtime code and compile time code in the Zig language. In compile time, every value has a static lifetime. This means that it is valid forever. It cannot go out of scope and be destroyed. It's very useful to think of this as garbage collection, although this is not true in the current compiler. Here we can see some examples of this behavior. For example, we are defining a function that is returning a reference to a buffer. And this is completely fine at compile time as opposed to runtime code. And of course, here we can see the same thing. We are taking references to variables that are defined in this function, and this is completely fine. So this is one of the core things that you have to keep in mind when working with compile time code. In addition to this, at compile time, one of the most useful features that can be used for a lot of purposes is slice concatenation. Here we have a simple example. We are defining a string of Unicode count points, and down here we are concatenating some U21 character. Of course, you should try to keep this at a minimum, because every time you concatenate, a new value is created, so some more memory will be used by the compiler. If you know the size ahead of time, it is better to define some array and just use the indexing and etc. But this feature is very useful, especially since allocators cannot be used at compile time, at least for most purposes. So this is some way to have, let's say, some array list type of construct without using allocator. The next feature I would like to talk about, which is relatively new and pretty obscure, is AnyType fields. So you can actually define a field in a container type as AnyType, and this makes the type of the field variable as well as its value, as always. This is a simple example. We are defining struct, which has an AnyType field. And as you can see, here we are concatenating tuples, so the type of the tuple is actually changing. This is not a slice, so the type itself is changing. And this example is just taking a tuple that will be passed to a format function and intercepting some Unicode code points and encoding them as UTF-8. So you can see how this is quite useful. If we didn't have this feature, to do something similar, you would need to probably create some recursive function that constructs a tuple and adds an element every time. But here we can just use iterative style and not worry about recursion at all. So one of the most important features that Zig offers is the type info built-in. This built-in takes a type and returns a description of this type, which is a type info value of the type stud built-in type info. And we also provide some helper function in the stud meta module to help out and reduce a lot of the boilerplate. This is something that you can see in most metaprogramming applications. It is very common to use type info to do introspection and compile time reflection. This is a very simple example where we are extracting some information from a function type. Here we are extracting the calling convention as well as the return type, which can be null, and the type of the first argument of the function. So you can see that this could be a little verbose. Here it's okay because we are doing relatively simple things, but the stud meta module provides a lot of tools to make this, to make some more complicated things way clearer. For example, here we are using the trait submodule of stud meta. We are checking if the type passed in is a struct with this very simple line. And we are iterating over the declarations and checking some stuff. And the same thing for the fields. These functions work with any container type, not just structures, but also unions. And I think enums for some of the functions where it makes sense. You can see that we are very simply unpacking an optional type if the type is indeed optional. And this is very clear and very nice. So in addition to type info, we provide the type built-in, which is exactly the inverse operation. So given a type info value, type will construct a type and return it. This feature has been recently extended to support structured types, or just structures with fields and no declarations. But this opens up a lot of cool things you can do at compile time. For example, you could parse some text, some format, and create a structure that corresponds to the domain-specific language that you have defined. This is a very simple example from a recent pull request. This has not been merged into master, but it is very nice for illustration purposes. This is a function that takes an iterable of types. So this could be a tuple with types or a slice of types, or an array or a pointer to an array of types. And you can see that we are defining the tuple fields. We want to return a tuple type of the types passed in. So we are defining the fields and iterating over the types we just give the names that we need. Like for a tuple, the names of the field should be 0, 1, etc. We don't have a default value. They are not comp-time. And here we are just calling the type built-in. And we are creating a struct and returning this type. So this is very nice, clear. And you can see how powerful this can be, since you can write arbitrary code here and deal with strings or embed some file and do some computations. This is just a very simple illustration, but it is very useful. Okay, so this one is a bit different. So this is a feature that varies a lot between runtime and comp-time code. So first of all, let's explain what pure type resolution is. So when you have an expression like an if-else expression or a switch expression or even catch or else, etc., the compiler will take all the possible values that can be returned from the expression and find a common type which can represent all the values that are returned. So for example, you could have an if-else that returns either usize or a comp-time int, and the common type will be a usize because comp-time int can coerce the usize. Now, this does not happen in compile time in a lot of cases. This is very surprising behavior when you see it for the first time. It's probably a bug that will be fixed in the future, but it is important to keep it in mind in case you're writing code that works both at compile time and runtime. So let's see an example of this. This is actually a bug from the standard library, which has been fixed, but it illustrates nicely what happens. So this is in a standard format, and the code is looking into the options to see if an alignment has been specified, or it uses left aligned as a default. Now, in runtime code, this option alignment field is of type optional alignment. So, and this is an enum literal, so it can coerce to alignment. And the type of alignment is alignment with a capital A. In comp time, when this is null, then the type of alignment will be enum literal. It won't be alignment. So the code switched on an alignment and tried to do some stuff, and this failed because the type was not an enum, but an enum literal. And here's the fix, very easy. You must specify the type directly, and everything works fine. But it's very tricky when you first see it. So yeah, keep that in mind. Here's a very fun use of this bug. So this code Andrew wrote in this issue, which takes advantage of this semantics and can actually detect if we are in a comp time context or in a runtime context. As you can see, you can do this very easily by just returning a different type in an if expression and checking what the final type is. So yes, of course, you shouldn't rely on this. This is totally wrong. Please don't code it. But, it's just to show you a semantic difference between runtime and comp time, and that's it. You should just know about it if you're writing comp time. One last hack that we can do at comp time is what we call comp time closures. So this is a way to capture some comp-time mutable state and to modify it through method calls or associate it with some object. You will see in the next slide, it will be clearer. This relies on using anonymous struct literals to avoid caching of functions, because the anonymous struct literals have different types every time they are created. In my experience, this can be pretty buggy in more complex cases, so I would probably avoid doing this, and it may be removed in the future, although it's not sure. There are some proposals that could make this type of code a lot clearer, but none of them are accepted. So for now, this is something that you can do. So this is an example from Zorro, which is a borrow checker written in comp-time Zig. So here you can see we are creating some state, comp-time state, which is captured in the struct that is returned by this function. And we are using this unique argument to avoid caching the read function, and we can have access to the state and modify it if we need to. This is just one part. So here is the second part. So here we are doing the same thing. The second argument of this function is also used to avoid caching, so that we get a unique instance of borrows and mute borrows, even if we pass the same t, same type. And we're doing the same trick here and returning the type we saw before. And here you can see how you can use this, and it works, but it's not the most elegant thing. So this was an overview of some compiler features. Thank you very much for listening, and please, if you have any questions, I can answer.
Okay. Thank you very much, Alex. Let's switch to the Q&A view. So, whoa, that was a lot of like very detailed information about how comp-time works. I think I also encountered the pure type resolution thing while writing my Redis client in the past. Thank you for explaining how everything works. I always just assumed it was like random bug in the compiler or something like that. But I see. Well, it is surprising. I agree. It's not a showstopper, though, right? I mean, you just have to pin down what the expected type should be, and everything works out.
Yes, you just have to be a little careful. Mm-hmm. But it's surprising for sure.
Okay. Let me see. So while people start typing down questions, let me see if there's a question that I can ask you to start. So I asked you already about how you started with Zig. So when are you going to start programming professionally?
I don't know. As soon as possible, I guess. But yes, I can't give you an answer to this right now.
I see. Well, I mean, my point is, it seems like you're pretty good at programming. So I have no idea how expert you are as a civil engineer. We can assume you are, but I mean, unless you are a super civil engineer, no, not really. Then you should totally find a way of switching careers. Okay, so first question from Matt Knight: did I see a cat? Is your cat with you now? I saw. Yeah, I also saw it.
Yes, she went away, but yeah, she was annoying.
Okay, so first serious question. So what plans do you have to utilize comp time for?
So I actually use CompTime in a couple of libraries that I use already, that I have written already. One of them is interface.zig, which is a way of implementing dynamic dispatch in Zig. And I use it to actually take some vtable type and automatically fill it from an implementation type. So some of the code earlier is actually from that library.
Mm-hmm. Let me make it bigger. Okay.
Yes, for example, here you can see I'm checking if the vtable type is correct. I also have written a compile time regex library, which takes the regex and a statically known regex and pretty much compiles it, well, at compile time, and it can match at runtime or compile time, but it is very much a work in progress. But of course, there are 1,000 applications I could think of. For example, I was thinking of implementing a protobuf. In compile time, you could take a protobuf file and create the structures, parse the file, find out what structure you can make, etc. Yes,
Mm-hmm.
you can do a lot of it.
Um, okay. Let me see other questions. Actually, let me first make you big again. Oop. Okay. There's a question from Andrew. Let me see. There's another one. Okay, this one is from Joachim Schmidt. Do you think comp time is strong enough for a maybe Rust-like borrow checker to be implemented?
So the code I showed actually implements a borrow checker. This is half of the code. You can also write the mutable borrow stuff. But of course, the usage is a little iffy. Like the user must call the correct functions, etc. You can't automatically just and taking a reference of the value just to check the borrowing. You have to call functions, etc. So it is possible, totally possible, but it's not. It won't be as nice as Rust.
Mm-hmm. So basically, the complete memory safety utopia only works under some kind of authoritarian regime where, right? So like this, the user might, like the programmer might forget to go through the borrow checker thing, and they could still
Right, or they can just access the value itself and do whatever, which obviously is not possible.
Yeah, but in any case, so go check out Zorro. So if you want to see it in action and see how it works. Okay, there's a question from Andrew that I also kind of wanted to ask, but the way I was about to ask it was a bit more, it was less impartial, I think, than him. So I'll just say his version. So, do you think we should allow declarations like decals in type and close issue 130?
So personally, yes, I would love it. And there are a couple of reasons. Like obviously, it will make it will allow a lot of new things. For example, you could actually implement C import in user space, like embedding a .h file, the parsing it, and creating a struct with the correct decals or stuff like that. obviously can make things a little more unclear, I guess, but I don't, uh, I don't think it's so much different than just allowing fields. If we can create fields programmatically, then we have already lost some clarity, if you will. You can just look at abstract, so I don't see why we should restrict type to just allow fields. But
Okay.
that's just my opinion.
About issue 130, do you know which one it is?
I don't
Do you
know
remember?
off the top
Okay,
of my
because
head.
Andrew just said issue 130 is the proposal to have any vtable language feature.
To have, sorry, what?
Vtable language feature. Well, if you are opening it, just open it and.
Right. Personally, I don't think this is necessary. I believe we can write this as a library and be even more flexible than other languages. For example, in Rust or in most languages, the way this feature is implemented is by using fat pointers. So you have one pointer to the vtable and a pointer to the implementation data. But of course, this is just arbitrary and you are locked into it. While using a library, you can do stuff like have different policies for how the vtable is stored and how the object is stored. So you can have, for example, some inline buffer of n bytes and store the object directly there, and avoid one indirection, etc. And I think it's more flexible as a library. Of course, it's a bit uglier, but I don't know. I think it's good enough.
So we have another question, but I think let me ask one first. So I think I remember Andrew saying something about one good reason for limiting slightly the power of type was so that instead of generating a bunch of machinery at compile time, the alternative would be to have some kind of step where you write down a Zig file programmatically, right? So you have the first step that creates a Zig file, then gets added to like a build step. Now, and I think one reason that he mentioned was because that way it will be easier for certain type of tooling to reason about this stuff. Now, one question about like tools like ZLS, or let's just say ZLS precisely. I don't know what the current situation is, but let's say, I don't know, a few years from now, assuming we have Z 1.0, is it reasonable to expect to have ZLS have basically a comp time running inside of it and being able to give out information about what the resulting state of running the comp time step is?
So I think this will be possible. And the way this would be implemented would actually be by running the compiler itself and using the internal information from the compiler, or by implementing some semantic server in the compiler. Without the compiler, this is extremely difficult. You basically have to re-implement a big chunk of the compiler. So ideally, the compiler would just support some program like ZLS or some other program would be a bridge in the compiler and the editor. And I think this is actually planned.
Okay, I see. Makes sense. By the way, for what it's worth, I'm almost of the opinion that not limiting type is the better choice. But I'll say one thing in favor of what I said earlier about the having a step where you write down in a Zig file you write programmatically into a zip file. Like if Go also has this approach. I'm not a big fan of it. I think it's clunky. But one big upside, at least of that being a possibility, is that way you can easily inspect what the result of like a, let's say, user space import is. Because if you don't have that step, then everything is somehow in the comp times memory, and it's harder to inspect. You can just scroll through it unless you have adequate tooling. So there's also that.
Yes, I completely agree, but in my opinion, the answer is to create tooling instead of.
Well, Andrew just mentioned, think about stack traces too.
Yes, I see what.
So
I guess it could get ugly.
I guess the answer, we want both. We want everything. No, I don't know. But anyway, food for thought. So the final question then, which I think we kind of answered at least partially with the comp time in ZLS question. The question is regarding to the comp time protobuf generator idea. Love it. Will ZLS be able to understand it, and will you be able to jump to definition, etc.?
No way. This is way too complicated for ZLS in its current state, at least. At the moment, the only comp time evaluation ZLS does is very simple generic types, or not very simple, but generic types, for example, array list or whatever. It can resolve what struct is returned and the type that you passed in as a parameter, but this is it. It can't do anything. It can't evaluate switches or if expressions or anything like that. For now, the tooling is lacking for sure for this kind of metaprogramming approach. But yeah, I think in the future we will have adequate tools to inspect the results.
Okay.
Help you out.
Yeah, I think this is a very interesting topic. I mean, I guess everybody loves metaprogramming. It is kind of addictive, and we have in our hands a somewhat unique metaprogramming tool. But metaprogramming can also go wrong, go very wrong. I'm sure everybody has experienced something like that. Of course, most of the time it's macros. But even without macros, it can also go wrong.
Yeah.
Okay, so let me see if there's any other questions somewhere else, but I think we are good. Yes, we are. So, Alex, I think I lost your webcam. Are you still alive? Alex? Ooh. Alex, can you hear me?
I can hear you now. Sorry.
Okay, we lost connection for a moment. Not a big deal. Okay, so any final statement that you want to make before we move forward?
Not really. Like, thank you for having me, of course, and everyone for watching, and have fun in your talk.
Thank you very much. Okay.